So, welcome back everyone for day two of the UAV workshop. And today we'll be carrying over the part that we were supposed to cover yesterday, but we'll quickly cover it today. That's the power plant section. And then we'll move on to an overview of how a UAV is controlled, water control systems, and how does a manual controller look like, and how can you make it an automatic controller. Okay. So today we'll be discussing power plants. We'll also be doing a sample design calculation for the aircraft that I have built, and how can you size the aircraft next time according to your needs when you build one. And then we'll move on to discuss about how a drone is controlled. So as I told you yesterday, that the power plant is composed of these three sections: the battery, the motors, the ESC, and the propellers. And what happens is, you have the battery pack, it powers the motors, it powers the ESC. The ESC takes inputs from the receiver or from the flight board, and then it sends a signal to the motor. The motor is powered by the battery pack but is controlled by the ESC. And finally, the motor turns the propellers to produce thrust. So how do you choose which battery pack you are going to use? So most of the battery packs that we use for drones are lithium polymer batteries. Why? Because they are very high in energy density. And secondly, that makes them, like, if you use a small volume or a small size of theirs, you get a really long flight time. Now, when you use a battery, you need to keep in mind three of the specific voltages that are very important. So the first one is cutoff voltage, then we have nominal voltage, and then we have maximum or full charge voltages. So if you see, I have provided a table. Number of cells, like, we denoted by 1s, 2s, 3s. So very basic fact that one unit of, maybe I could show you this. Yeah. So I think if someone does not know, then one unit of this one unit is called a cell, and a group of units, a group of cell units, is called a battery or a battery pack. So how many cells are there in a battery pack is denoted by this symbol. It's a number uh, followed by S. So 1s, 2s, 3s, 4s, 5s, 6s, they all mean that, like, these many number of cells in that battery pack. Now, all the LiPo batteries that we use, generally, they standard have a 3.7 voltage per cell. And if you have one, two, three, then they are all connected in series. So basically, the voltage is going to keep on increasing. Okay. So now what happens is, when you have a battery, why do we need a battery? A battery is supposed to be a constant voltage source. We want the voltage to be almost constant. So the battery does provide constant voltage during all of its operation, but we must keep in mind that as the battery discharges, there has to be a minimum voltage beyond which we should not discharge the battery, and that is called the cutoff voltage. If you discharge the battery below the cutoff voltage, you will mess up the battery, and the battery will not be able to recharge back to its nominal voltage. So let's say you bought a battery pack for 3,000, 4,000 rupees, and it was rated to be operated at, let's say, 11.1 volts. You discharge it below 9 volts, you will not be able to use you'll not be able to use the battery to power the same motor again. So it's a complete loss of 4,000 bucks. And then there's also the maximum voltage. So if you charge the battery beyond the maximum voltage, then you are potentially going to cause a fire. So avoid that as well. Both of the things destroy your battery. So overcharging and discharging LiPo batteries is overcharging is going to create a disaster. And under, like, if you over discharge it, then it's going to be a problem. You won't be able to reuse it next time. um Basically, how do you choose what battery pack you are going to take? That depends upon what motor you are going to use. We'll discuss about motors next. So the voltage rating of the motor is going to tell you what voltage of a battery pack do you need. Okay. Um, a motor and a ESC combination is more suitable, because again, the ESC also has to be suitable for the battery pack. ESC will discuss what is an ESC. The capacity of a battery is measured in milliampere hours. Milliampere hours is simply a unit for charge. Higher the capacity, more flight time. Then something that is important with respect to batteries is the discharge rate. How fast can you take up energy from the battery? So there are two kinds of discharge rate. One is called the continuous discharge rate. The another one is called the burst discharge rate. So continuous discharge rate is where like you can draw this current regularly from the like from the battery divided by the battery capacity. That's give you the continuous discharge rate. Okay, and it's measured in C. It's called the C rating. So basically, let's say the maximum current drawn is roughly let's say 30 amperes, and the battery capacity is 5200 um, what do you say, milliampere hours. Then you can divide it and you'll get a unit for charge, and that is going to be charge, basically it's current and it's going to be per second. You're going to be like, I'll just do a small example. So let's say the maximum current drawn is 30 amperes, and let's say the battery capacity is 5200 milliampere hours. Then your continuous discharge rate is simply going to be 30 amperes divided by 5200 milliampere hours. So this is going to be 30 amperes by roughly 5.2 ampere hours. So this is roughly going to be 6 um, per unit hour. So this is the discharge rate. Similarly, you have something called a burst discharge rate. So burst discharge rate is, let's say you are going to make an acrobatic aircraft, or let's say you want to make a flip turn with a quad rotor. Then there is something very important there. What is important? The moment you want to make a flip turn, you suddenly want a lot of force, on two motors. And, again, when you make the flip and when you want to you want to stabilize, you again want a lot of force, to stop that jerk. So it is during these moments that all the four motors will be drawing a lot of current that may be beyond this continuously provided maximum current. So there is provision that your battery can supply, more current than its rated current, but then the maximum burst current has to sustain only for a small amount of time. It is suggested that the maximum burst current should not last more than 5 to 6 seconds. Like if you want to take the extreme limit, that is why I mentioned 10 seconds. But I'm telling you, with my practice, burst current should not last more than 5 seconds. Although a lot of places they'll write 10 seconds, but take it from my personal experience, it's not going to last more than 5 seconds. After 5 seconds, your battery is going to like suffer damage, your motors are going to suffer damage. And if you want to do acrobatics, then remember that two sharp maneuvers should be, evenly spaced in time. If you are doing too many sharp maneuvers one after the other, your motor is going to heat up and your battery is also going to heat up, damaging both of the things. So again, how do we choose a battery pack? How much current? Basically, you need to sum up what current your motor is going to take, what current your flight board is going to take, what current the servos are going to take. So all the electronic items on board, how much current they're going to take, sum them up, take some factor of safety. What is factor of safety? So let's say you sum up all the currents you get, let's say at a time, the whole system running at its full power is going to take 40 amps. So you take a factor of safety of 1.1. So you choose a battery pack which supplies 45 amps or 50 amps. And what that ensures it, let's say one of the components on your flight malfunctions or does not function properly or gets shorted, then what is going to happen? Your battery is will be able to provide a little bit higher current for some time. Your battery is not going to, blast off after 40 amperes. um Battery size, then again, if you have a bigger battery, like basically the capacity increases the size. Obviously each cell, every lipo cell is roughly 3.7 volts and 3600 mAh or around 3000 mAh. So what is going to happen is, if you want like a longer flight time, you want a bigger battery, but then a bigger battery comes with larger, like more weight. More weight is going to reduce your flight time because it like It is going to, it will need more lift. You will need more lift to be up in the air. If you need more lift, you need more velocity. If you need more velocity, there will be more drag. If there is more drag, the motor needs to consume more current to run at a higher speed. So it is all a trade off. Okay. Everything is like everything comes out to be a trade off. I said this yesterday also. Battery voltage has to be compatible with the available motor and the ESC options. The battery C rating. This is very, very important. You need to look at your motor and see that how much current does it draw at 100% throttle, because we rarely keep like fixed wing flights, even like other than we take the quadrotors to 100% throttle a lot of times, but we rarely take the fixed wing aircrafts to 100% throttle a lot of times. So we do not take them. So you must see that the maximum discharge rate of your battery is able to match the maximum current that is required by the motor at 100% throttle, because that is the time it is going to require maximum current. And then what kind of battery connectors do you want? So, I have shown different types of battery connectors that are available in the market. And then these connectors have certain limits. So you have to operate these connectors within these limits. And if you look here, there is this device. If you see this, I'm sorry. So if you look at here, this is this device, which has basically 3 digits. And this is connected to a 3 cell battery. So what is happening is here this is called a balance detector, or a balance, voltage balance detector. So what is happening is you have 3 cells in series. They are providing voltages. So when you charge them, you need to ensure that, let's say you are making a battery pack of 3 cells with each 3.7 volts. When you recharge it or whenever it is used, you want that they equally discharge and equally charge. So to check that if that is happening or not, you need a balance detector or charge balance detector. Periodically, you need to keep checking the health of your battery. So all the batteries that you see, they come with 2 terminals. If you look closely, so this terminal goes to the power or discharge terminal, and this is the balance terminal. So this is called a DF14 connector or a JST13 connector. It depends upon what kind of battery you are using. These are like very specific terms when you want to buy stuff online. These terms will be very important, because if you buy a DF connector for a GST port, you're going to simply end up wasting money. Moving on next, let's talk about motors now. So we all know that in robotics we mostly use DC motors. We do not use AC motors, and the reason is that we mostly power like the robotic items that we make are mobile, and we use battery packs, and battery packs do not provide AC current. They generally provide DC current. You can obviously make it an AC current by putting an ADC, but why do you want to take that when you can do a lot of stuff with the DC? So DC motors, there are 2 kinds of motors: brush DC motors and brushless DC motors. I'm not going to go into the specifics of what how does a DC motor operate, or how a brushless motor is going to be different from a brushed motor. You are more than welcome. I am going to show you next slide. There is a YouTube video by the channel. I guess the channel is called, okay, I think it's in the EFC section. I'll show you there itself. So there are 2 kinds of brushless. So in drones, in large drones or in medium sized drones, we use brushless DC motors. In very small drones or in micro FPV drones, we use coreless motors or brushed coreless motors. If you want to go into depth, you can just Google up these terms. Um, for drones, we mostly use BLDC. BLDC is of 2 types: in runner and out runner. The the ones that we use for drones is the outrunner one. Okay, why? because in runner PLDC motors run at higher speed, but they have lower torque. And then outrunner BLDC motors have higher torque, but they run at lower speeds. So yeah, that's the thing. Uh, Moving on, how do you like what is critical in determining what kind of motor do you want? So first of all, the most important thing that you need to keep in mind is the thrust to weight ratio. Okay. So for fixed wing UAVs, your thrust to weight ratio should be 0.5 to 1. So let's say you're going to lift 2 kilograms of mass into the air, then your thrust should be around 1 kilogram to 2 kilogram. And if you are going to, use a rotor wing aircraft and you want to lift 2 kilograms into the air, your thrust should be around, 4 to 6 kilograms. So you must have seen that fixed wing RC aircraft use one motor, whereas quad rotors use four motors. And if you want to go with a racer rotor wing, then you need to have an even higher thrust to weight ratio. Second thing that is important is the kilovolt, not the kilovolt, it's the kV rating. So it's not called kilovolt. It does not mean kilovolt. Please don't make that mistake. A lot of people have this misconception that kV rating means kilovolt. No, it's 1000 per volt. That is how you read it. I'll repeat it once again and I'll write it down very explicitly that this kV simply means 1000 per volt. That is, if you apply, let's say one, so let's say if you have a 1200 kV motor, okay, and you supply it a voltage of um like basically 1200, like it's a 1200 kV motor. If you supply it with 1 volt, it's going to spin at 1200 revolutions per minute. Okay. If you supply it with 10 volts, it is going to run at 12,000 revolutions per minute. That is what this kV rating means. So RPM is thousands per volt. Okay. Mounting propellers. So now what is going to happen is if when you mount propellers on the motor, you are introducing a load on the motor. So I don't know how fairly you remember the basic, like I think it was electrical sciences, which is taught in first year. There were two things, DC motor running on its own and DC motor under a load. So when you put on a propeller, the propeller is cutting through air and it's pushing air. So the propeller is doing a significant amount of work and, you know, it's transferring energy into the airstream as well as it's rotating on its own. So that energy has to come from somewhere and that obviously comes from the motor. So the load is going to increase and the RPM it's going to reduce. Okay. Now, what kind of propeller or what kind of motor do you want? So if you want a high, let's say a high torque motor, then you should use like basically lighter, basically torque determines the load and what current you are going to take. So basically if you want to use bigger motors, use smaller propellers. Okay. When the propellers are small, they spin fast, produce the same amount of torque. And if you have smaller motors, you can use bigger propellers. Okay. So uh, if the RPM is really high, then use smaller propellers. If the RPM is low for the motor, then use heavier propellers. um Too much, obviously too much high current can overheat the motor and the coils with wear. How do you like basically decide on a motor name and how do you select its size? So let's say a motor is sold as the motor that I have used in my RC aircraft is A2212245. I'll just write it down in a more clean manner. It's A221222450 kV motor. Okay, so the A is a series of the company that makes it, that has no like special significance right now. 2212 means So it has two parts, 2 2 and 1 2. 2 2 means that the stator, okay, the stator has a diameter of 22 mm, and okay, and the stator height is 12 mm. Okay, that's how you specify the motor. Uh, and this stator dia and stator height are going to determine how much torque you are going to get at a certain RPM. Okay, if you have a taller stator, it will be able to cut through more magnetic field and the heat dissipation is better. If you have a wider stator, then you have so taller is basically taller in this direction and wider is in this direction. Okay, so if you have a wider stator, you have a bigger radius arm, you have better torque. Okay, but again, if you keep at the same height and if you increase the width, you are going to be using more energy, right? But the efficiency is more or less going to remain the same. Okay, so it is going to dissipate heat, a lot of heat. And then if you want to increase heat dissipation, make it cooler, then you make it taller. Okay, small drones use brushed coreless motors. I just wanted to mention this here because lot of times, okay, I'll repeat the 2212 significance in a short one. I'll just give you a better diagram for that. Okay, so smaller drones use brushed coreless motors because many times people think that brushed DC motors are useless. That's not the case. Brushed DC motors are just not useful for drones because here the motor has to turn very fast and a lot of times, and we need high RPM. If you want to drive a car or an RC car, it does not spin very fast for very long times. You steer slow, you go slow. So you need very high torque there. You don't need very high RPM there. Here we need very high RPM and very less torque. Okay. So yeah, I'll just repeat the significance of this A2212 once again. So if you just look at this picture here. So this is the stator part of the what do I say? The stator part of the motor. Okay. And there is a rotor part of the motor. I don't know if I'll be able to show you here. Yeah, I think it's here. Okay. So what you are seeing, so this is a brushed motor. Don't worry about this. Okay. I'm just asking you to realize how a stator and rotor looks like. So I think here, yeah, this is better. So this the thing on the inside is the stator, this part. This part is the stator. It remains stationary. Okay. These connections that you are seeing, they go and connect to the stator. There are three coils. Okay. Three coils. So the a brushless DC motor, the diagram for a brushless DC motor is something like this. These are the three coils. Okay. That you are seeing. I don't know. This is, let's say, this is coil A. This is coil A. This is coil B. This is coil C. This is again coil A, coil B, coil C, coil A, coil B, coil C. Okay. And now what is going to happen? How this brushless DC motor is going to work? We are going to excite these coils one after the other. Okay. And that is going to attract or repel. So let's say that right now we induce a north pole here and a south pole here on coil A in this one. Then what is going to happen? This is going to attract and this is going to repel. So what is going to happen? The outer circle, the outer one, that is, so this part is free to rotate. So this will start, sorry, I should just make a different symbol. So this is going to attract and this is going to repel. So this is going to turn like this. That's how a DC motor works. Okay. Now what A2212 means, is basically, this is the stator part. The rotor part has been removed. It's like it slides on and slides in. Okay, so this is where the shaft goes. Okay, and then the whole rotor part is housed on top of this like this. Okay, so now this thing, this height, should I use a red one? That is better. This is called the stator height, as is shown right here, right? Here, here. This is the stator height, and this is the stator width, right? So stator height is going to determine the area, right? The area that you are going to, like basically this area is going to experience magnetic force, right? So the stator height is going to experience the stator height into this portion. So this is roughly constant. That is dependent upon how many cuts you make in it. But then that area, okay? And then stator width is basically, it's the radius arm. So you have the rotor moving outside. So stator width is going to basically tell you or decide how much torque you are going to get. So when I have a motor called A22122450 kV, these four numbers are basically telling me the dimensions of the motor. How are they telling me the dimensions of the motor? Sorry, the dimensions of the stator in the motor. Okay. How are they telling me the dimensions? The first two digits, 22, basically give me the diameter of the stator in millimeters. Okay. So if this was an, if this was an A22122450 kV motor, then basically the stator width will be 22 mm and the stator height will be 12 mm. Is this clear? Great. So moving on, finally we come down to propellers. So for fixed wing aircrafts, the propellers. So first of all, I told you that propellers spin and they are going to generate thrust. How do they do that? For that, you need to know blade element theory, momentum theory, and then finally you need to study blade element momentum theory. Now, what kind of propellers do we practically use on a fixed wing aircraft and rotor wing aircrafts? So the size is the most important one. Okay. The diameter, the pitch is roughly the same. Like you'll get restricted options for pitch. It's the diameter that you need to play with. Okay. So for fixed wing aircrafts, propeller diameter should be 4 to 6 times the maximum fuselage width. Why this is so? Because this is only for the propellers or for motors that are mounted on the nose of the aircraft, like the one that I showed you yesterday on, like on this RC aircraft. So if the motor is mounted on the nose of the aircraft, then obviously the air that the propeller is throwing backwards is going to hit the fuselage directly. And if a lot of that airflow is being blocked by the fuselage, your thrust will greatly reduce. Okay. You will not observe the thrust that has been given in the specifications sheet, which we will just see a sample of soon. If it's mounted on the wings or away from the fuselage, then you just need to keep in mind, because the like it happens generally in the aviation aircrafts, the engines are mounted below the wings. If you want to mount the propellers like that, then the propellers do not face much resistance by throwing the thrust backwards, because they have a very streamlined body behind them, right? Now what happens is, if you want to mount these propellers or motors on the wings, you just need to keep in mind that the propellers should be quite far away from the fuselage or the wing root. The propeller should be at least, the propeller tip closest to the fuselage wing root where it is attached. It should be at least half of the propeller diameter, or that distance should be propeller radius. For rotor wing aircrafts, the propeller diameter is dictated by the frame size. There are two things you need to keep in mind. Basically how big the frame is, depending on that, obviously the first matlab, the most trivial geometrical constraint that you can put on propeller size is obviously the propeller should not hit each other, right? That is the most trivial geometrical constraints that comes into one's head. However, when you look at the aerodynamics, it's much more involved. If you put two propellers side by side, their airflow is going to interfere with one another. So you want to minimize that as well. That is why what we suggest is that we maintain minimum half length of the propeller diameter from one propeller tip to the adjacent propeller tip. Okay. Otherwise, again, you're going to have a significant reduction in your thrust, and also your motors will not be operating like at proper efficiency because there will be quite an amount of interference from the next motor. How are propellers tagged or labeled? So let's say you went to the market and you said, "Ki, I want a pair of propellers." First of all, propellers are always sold in pairs. Can anyone guess why? Like they can be sold in single units also, but propellers are generally sold in pairs. Why? Can anyone just give it a guess? Yes, clockwise and anti-clockwise motion. Exactly. So basically, propellers are going to have a pitch and a diameter. What is a pitch and a diameter? So basically, diameter is the enclosing circle of the propellers, and pitch is how basically, yeah. So if you take clay, let's say if you take clay, okay, and you make one revolution of your propellers, you put the propeller on the starting of the clay and you twist the propeller once, one full revolution, then you will see that the propeller digs inside the clay. Okay. And as it digs inside the clay, it moves some distance. That distance is called pitch. Okay. So basically, it's the like if you turn the screw once, the screw is going to move inside the wall or the wood, whatever, wherever you're putting the screw. So one revolution, how much length it turns, it goes inside, it's called the pitch. So all the propellers are tagged or labeled using their pitch and diameter. So if you have a propeller labeled 1045, then it has a pitch of 10 inches. Oh, I'm sorry. This is wrong. In my PPT, I have written that this is pitch and this is diameter. This is wrong. This is the diameter and this is the pitch. I'm extremely sorry for this mistake. So prop 1045 has 10 inches of diameter and 4.5 inches of pitch. Sometimes on some websites or in some stores, you'll see that the prop is labeled as 10 cross 4.5. That is even easier to understand. You only need to keep in mind that the diameter always comes before and the pitch always comes, and the pitch always comes later. Now, basically, I told you that to select a motor, you need to have a proper thrust to weight ratio, right? So now how do you determine how much thrust a motor propeller combination is going to give you? You do not have the luxury to buy all the motors and all the propellers and then put them on a test stand and see how much thrust they are giving you. So for this, we use data sheets provided with motors. Okay. So you choose when you look at the motors. So see, everything is an estimate now. Okay. When you want, we'll do a sample design calculation after this, and you'll see that how much guesses we make, and it generally turns out to be correct. That's because you need to do a market survey or a survey of what possible options you have. So you make a possible options that you look at possible options of what other people have used as motors in the same class of aircrafts, and now you go and look at the data sheet. Okay, so this is the data sheet of the A22122450 kilovolt. Now look carefully. This is how you read a data sheet, and it is very important that you learn how to read a data sheet of motors. Otherwise, you won't be able to select which propeller to use. Okay. So now it is giving you that the A2212 motor, 22 stator dia and 12 stator height. Okay. It comes in these variants. It comes in 930 kV rating, 1000 kV rating, 1400, 1800, 2200, 2450. All of the operating voltages 11.1 volt. Can someone just put me in the chat or tell me in the chat, if I am to use 11.1 voltage as the nominal or operating voltage, how many cells of batteries do I need? Or the battery pack should have how many cells? I'll just refresh your memory. Yeah, three, exactly. So all the lipo cells generally, means there will be very rarely a lipo cell which is going to give you a different specification, but it has almost become a standard that all the lipo cells are somewhere going to have 3.7 to 4.2 volts, and the capacity that each cell has is roughly 2800 to 3600 mAh. So 11.1 volts means three cells. Yes. Now the next column that you see is called prop. Okay. So now they have suggested that with the 930 kV motor, you use the 1060 prop. With 2450 kV motor, you use the 6030 prop. Okay. So you can, also use another prop on another kV motor, but it's fine. Like these are the data sheets that is provided by the company. You can also estimate if you wanted to use a 1950 or a 1060 with 2450, you can also, find that online these days. There are calculators or data sheets or people who have experimented on all the ranges, and you can simply find the data there. Yeah. Now, again, I told you that it is very important you find out what is the load current. Why it is very important to find out what is the load current? Because your battery is going to supply these currents. And if these currents turn out to be maximum, more than the maximum rated discharge rate of your battery is going to blow out. Okay. And this is the pull, or this is simply power, how much power it is consuming. And then this is the pull. This is the thrust that these motor and propeller combinations are producing in grams. So basically, if you use a, let's say if you use a 1800 kV motor, supply it with, I'll just make some written calculations so that it is easy for you. So if you use a 1800 kV motor, supply it with 11.1 volts, then at what RPM is it going to run? 1800 into 11.1. That comes out to be 19. That comes out to be 19,980 RPM. It's quite high. Okay. And what propeller is it suggesting? It's suggesting that we use the 8060 propeller. Okay. Then the load current is going to be 20.8 amperes. The power that it is going to consume is 231 watts. And the thrust that it is going to generate is roughly 0.805 kilograms. And if you want to take this in force or newtons, just simply multiply it by 10 approximately. So it's going to generate 8.05 newtons of thrust. Okay. And obviously, this is giving you the efficiency that, how efficient these motors are performing, that for the amount of power that they're consuming, how much thrust they're producing. Yeah, lipocell. Wait. Okay. So the weight of all these combinations, so weight of all the motor propeller combinations is constant. So this is how you read a data sheet. And now let's say I told you that I'm going to make an aircraft that is 2 kilograms. We are going to do a sample design calculation ahead. So I told you that we have an aircraft that is going to have 2 kilograms of 2 kilograms of what do you say? 2 kilograms of takeoff weight. It's a fixed wing aircraft that we are going to design. So what is the thrust to weight ratio that we can take? It is roughly 0.5 for fixed wing aircrafts. We can start there. So we can use the combination, we can use this combination, the 910 one. So we'll move forward with the 1400 and 9050 propeller. Okay. And then we go ahead and make our design calculations. Then I've also provided another data sheet if someone wants to look at how. So this is a much more diverse data sheet. If you look at it, they have like basically taken one motor, that is the 4012 320 kV motor. Okay, they have fixed the motor, the kV rating, and the stator height and stator dia, and now they have tested it against various propellers. Okay, and this is a much more detailed sheet. Why do I tell you so? Because here they're also telling you how much throttle, at what throttle you are getting the thrust, what kind of thrust. Okay, so this is a much more detailed data sheet, and this motor is obviously going to be costlier because it is a much well tested motor, right? So that is how you select a motor propeller combination. You want to find, you decide what kind of aircraft you are going to make. You make a survey of what other aircrafts are there in the market. Then you find out the rough weight that you are going to take off with, which is going to be for the for the aircraft that we'll be looking at. It will be 2 kilograms. Keep that in mind when we do the sample calculation. And as for that, we are going to use a motor which is going to generate roughly 900 grams of thrust, or 0.9, um, basically 0.9 kilograms of thrust. Okay, that is enough to help a fixed wing aircraft of 2 kilograms take off. Okay, so now we talk about ESCs. What are ESCs? ESCs are electronic speed controllers. Um, so basically, your brush DC motors, they have they have basically, so you all have used DC motors in your childhood, I guess. You used to take a 9-volt battery, and to check if a motor is working or not, you used to attach its two terminals to the battery. I think you guys have seen that. Is there anyone who does not has not used such kind of a motor? Then please tell me right now. Okay, can someone just respond that they have seen this kind of motor? Because no response seems quite dreadful. Yeah, people have seen. Okay. So this is a brush DC motor. You just have two terminals coming out of it. One is positive, one is negative. You attach it to the battery. The battery takes so basically now there are carbon brushes inside, right? And then it is attached to a commutator, and it spins the DC motor. So this is a brush DC motor. However, the brushless DC motor is a three-phase motor. Okay, it has three independent sets of windings, which have to be powered in a timely manner or in an organized step-by-step manner to make the motor turn. Okay, and since there is no rubbing parts, it's frictionless. Okay, it lasts longer, and but we need a controller to run the motor. That is the drawback. You have extra hardware here now to control the motor. um So it connects motor to the battery pack. What is the job of the ESC? It connects the motor to the battery pack, and it connects, the motor to the receiver. So basically, there is going to be two connections to the motor to the receiver, and it's going to power. It's going to distribute power between the receiver and the motor. Okay. The receivers or autopilot both can communicate directly, cannot communicate directly with the motors. Why do you think so? Can anyone just give me a reason that the receivers are the places from where your transmitter will be sending the signal to the receiver or the autopilot board. They generally can't communicate directly with the motor. Do you know the reason? It's not probably, it's because the fact that motors are of various sizes, various ratings, right? But your receiver and your autopilot boards all run on 5 volts or 3.3 volts. They have fixed power ratings, and the motors have a vast array of power ratings. So it's impossible that the receiver or a flight board can be directly compatible with an it's not that you can't run, it's not that you can't run them, but if you have to like explicitly make voltage converters and stuff like that. You can't run them without an ESC. You can have a separate throttle control, you can have a separate BEC. And you can BEC is battery elimination circuit. I'll also talk about that. So there are two types of ESCs. One is for brushed and for brushless. For brushed, we do not generally use an ESC. For brushless motors, we use ESC. So how do ESCs work? They basically transmit timed electrical signals to the motor. It's called, I don't know if you guys have come across this term, but if you have not, it's like I can't discuss it right now, otherwise we'll be losing out on time. But you should know that these signals are called PWM signals, or plus pulse width modulated signals. These signals are responsible for running almost all kinds of motors: servo motors, DC motors, brushless DC motors. So how does a signal travel? So the pilot on the radio transmitter is going to send a signal to the radio receiver, and the radio receiver picks up the signal. It sends it to the flight board, or it can also directly send it to the ESC. If there is manual control, then the radio receiver sends it directly to the ESC if it is being manually controlled. If there is automatic control, then the signal passes through the flight board, and then there is the ESC controls the motor. That is how your motor is controlled. The BEC basically eliminates the battery. So this is called a battery elimination circuit. Okay. So basically what it says is, so there are two types of signals when you are working with electronic items. Okay. A very rudimentary concept. There are two types of signals. One signal is a power signal, and one is a data signal, or let's say a control signal, and one is power. So basically you can directly feed. So if you look closely here, the receiver is directly feeding the throttle control circuit because it's the control signal. But the receiver also needs to have a power of its own. Right. For that, you need to use a separate power source because the receiver does not operate at the voltage of the motor. So for not having an external or another power source for the receiver, we use the battery itself. But to bring down the power to that level, to voltage to that level, we need a battery elimination circuit. So what does ESC have on the inside? So as I was telling you, if you're really interested in understanding how BLDC motors work and how ESCs are used to control them, please go and check out this video by this channel called The Engineering Mindset. It's an awesome YouTube channel if you are into engineering stuff, DIY stuff. And basically, it's a pair of three MOSFETs that is inside an ESC. You can also make your own ESC using basic elements. This channel also has a video about that. And I would strongly recommend trying to understand how BLDC motors work. So basically, here an Arduino has been shown. So this is nothing else but your receiver or flight board. Then that sends a signal to the controller, which is a PWM signal. Okay. And now the controller, using the logic that has programmed into it, the firmware that is programmed into the controller, it controls this three pairs of MOSFETs. Okay. And why I'm calling this three pairs? Because each pair is responsible for the activation of one of the three coils in the motor. And that is how an ESC operates. How do you want to choose your ESC for your drone? You again have to look at the current rating, the voltage rating, the size, and the weight. Also, what kind of ESC firmware do you want? So I'm not going into much detail here because this is similar to choosing, like basically if you want to choose a motor, the ESC automatically gets chosen along. You don't need to, fret your mind a lot about that. So if you want to go in detail about this, you can simply check out the YouTube video link, which will be posted today. So day one's YouTube video link is already active. I have not circulated it yet, but you can find it on the web. And today's link will also be provided with all the PDFs and the PDF slides and yeah, the PDF slides and the YouTube videos, the recorded sessions. So yeah, what is important is again, your ESC should have a BEC. I suggest that I have written that do you need a BEC or not. Many a times, if you work at specific cases, you might not need a BAC inbuilt into an ESC. um, but most of the times when you are starting off as an RC enthusiast or as a young aviation experimentalist, you can use BECs, BEC already loaded BEC, like ESCs who already have BECs. These are some of the ESC protocols that I have enlisted here. These are the ones that are being used currently. Now, what is an ESC protocol? ESC protocol is nothing but, let's say, the firmware language that ESC uses to communicate with the motor, or let's say the signal that the ESC sends, basically the controller sends to the motor or receives or gets from the control or gets from its receiver. So basically, PWM is the slowest kind of signal, although it's quite fast. And then there are faster protocols than that. I just listed them here so that you have a direction if you want to explore ESC protocols. If you are an advanced person who's already had some encounter with drones and you are experiencing latency issues in control by your ESC, then this is the thing you want to work on. For example, if you want to make a very, very fast turn, right? Your ESC should be able to send signals very quickly to your motor. Like if you want to do an acrobatic turn and use a conventional ESC or a cheap ESC, you won't be able to do it because that ESC won't be able to send signals very quickly to that motor. And the motor will basically take a turn and fall down, or it will lose a lot of height because then it has to sustain height also. So you need to use a faster ESC, a ESC which uses a faster protocol. So all the protocols that are listed from top to bottom are increasing, like are basically an increasing, their fastness increases or their latency reduces. How do you calibrate an ESC? So basically, I'll show you how to calibrate an ESC today in the demo itself while I'm showing you the manual control. And basically, you need to switch on your transmitter. You need to keep your ESC switch off. Um, you need to put the input from the transmitter which is going to be given to the BLDC, that should be on high full throttle, and then you connect the ESC to the battery. The motor will beep within 2 seconds. Bring the throttle down to 0. The motor will beep for 3 times, 2 times. The AC is calibrated. So basically you are giving it the maximum and minimum points on the input stick, and that will determine, like, that is how you calibrate your ESC. Your ESC now knows that this is the maximum your stick can go and this is the minimum your stick can go. So basically I'll show you. So this is a RC transmitter. Okay. So basically this channel is mostly used for sending throttle signals. So basically you switch on the transmitter, take this to high, then switch on your ESC, connect your motor. The motor will beep. The motor will not run. Don't worry. The motor will not start spinning and full throttle. Okay. Then what will happen? You then within after the motor has beep for beep beep, like it'll do 2 times, swiftly take this back. Don't leave it in the center. Okay. Just take it back to 0 again. Okay. And that is where your throttle is going to be 0. Then the motor will beep again, beep 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 3 times. The AC is calibrated. Now when you release this stick, the motor will start spinning. Okay. We'll see this in action today. So are you guys ready for one sample design on how do we design an aircraft? So I'll do the sample calculations for you. So we have a Just increase the pen thickness. So we have a target takeoff weight of 2 kilograms. Okay. And we want to lift this much in the air. We have already selected our motor propeller combination. Okay. Let's use the Martin motor. Okay. So we look at Martin motor and what is the thrust? So we want that roughly at around 50% throttle, I should be able to have 1 kilograms of thrust. Okay. So at 50% throttle, so my thrust, I'm looking at thrust. So this is 620, 970, 1330. So I'll go with 970 and 50%. So this is awesome. 1660. So my motor prop combination it says it's a Martin 412 320 kV motor with a JXF 1660 prop. And what is it doing? This is providing me 0.97 kgs of thrust at 50% throttle. Okay, so I don't need to use full current of my battery, just to keep the, like if you want to keep your aircraft cruising, you obviously don't want your battery operating in maximum current. That makes no sense, right? When you want to take a turn or when you want to do acrobatics, that is when you want your battery to be, throwing out the maximum current, or your motor, sucking the maximum current. When you are in simple cruise flight, you don't want your motor to be sucking maximum current. So you want it 50% throttle. Now, how do I design or how do I choose the wing? So yesterday I told you that you want to look at the different wings. Like you'll have to do a survey of what are the different wings available. And you will see that most of the RC wings that we choose are from the, so if I talk about wings now, right? If I talk about wings now, so we are going to choose from the KFM family, as I told you. Okay, so we choose from the KFM family, and now we can go to the slides that we had yesterday. So now you can see what kind of airfoil do you want to use, and uh, I can give you an estimate. So obviously this comes after a lot of reading and referencing. So you can take your initial lift coefficient to be like at zero angle of attack. Your lift coefficient should be somewhere around 0.5 to 0.8. We will still take it on the lower side. For our calculation purposes, we will take that CL is roughly equal to 0.6 at 0 AOA. Okay. So now what is the lift? The lift is going to be half rho V square C B CL. What is rho? Rho is the density of air. V is the cruise velocity, which again by survey comes out to be roughly 15 to 20 meters per second for the simple trainer craft that we are using. Yeah, there is a standard term for the aircraft calculation we are doing. We'll call it a simple trainer. We call it a simple trainer aircraft model. Okay, you can look it up. So when you have a design in mind, it's probably the case that someone already living on Earth or who is dead has made a design similar to yours. Okay. It's going to be very rare that you have come up with a new fuselage frame. If you have, you're going to make a lot of money out of it. But yeah, if you're thinking of some crazy fuselage idea or some, out of the world fuselage idea, someone has already built it, I'm telling you. So yeah, so you can, Google it up and find out that at what velocities these are going to cruise. And now I don't, so this is the chord. This is the chord length and this is the wingspan, and CL comes out to be 0.6. So if I want to keep my lift at roughly 2 kgs, which is obviously, if I talk in force, which I should be, is roughly going to be 19.6 newtons. From that calculation, you will just see that your C times B comes out to be 2 into 19.6 newtons divided by um, 15 square into, why am I taking 15 square? I obviously want that at low speed my aircraft still should be able to fly, into CL is 0.6. So if I put this into my calculator, gives me 15 square. Am I missing out something? Then just, yeah, I'm missing out the density. So it's going to be into 1.225 kg. So this is in meter per second whole square. This has no unit, and this has kg per meter cube. So I guess if I multiply this, do I get it? It works. Yeah. This is going to be meters square. Yeah, it works. So 15 square into 0.6 into 1.25. Well, so awesome. It comes out to be, so C times B roughly comes out to be 0.24 meter square. Okay, it comes out to be 0.24 meter square. So if you look at the respective chord lengths, or now the question arises that how do you choose the chord? Right now you don't know the chord, you don't know the wingspan. You have this crucial information that your area of the wingspan, you have gotten the wing area, right? But you don't know the wingspan and chord individually. Okay. So how do you like find out what chord should I take or what wingspan should I take? So now you look at aspect ratio. Okay. Aspect ratio is going to tell you how sleek your wing is going to be. So for simple trainer aircrafts, again, you have to look up the data. This aspect ratio is somewhere in the range of 5 to 8. Okay. High aspect ratios always provides better performance in low speed flight. Why this is the case? Aero student should know. Other people want to dig in, then they can simply go and have a look. Anyways, high aspect ratios always provide, like most of the time will provide better flight. So I take it to be 8. So basically what it's telling me is if I take the, so what is, I am assuming the shape of the wing to be a rectangle, not to keep it very complicated. So the aspect ratio, so this is C, this is B. So aspect ratio basically is BC, that is the wing platform area. So aspect ratio, it comes out to be basically, it comes out to be wings, it comes out to be square of the wingspan divided by the area of the wing. So this comes out to be B by C. Okay. So you will see that now we have, we can put B is equals to 8C, and 8C times C is going to be 0.24 meters square. If I solve, then I guess um, C square is going to be 0.03 meters square, and root over 0.03, 0.15. C is going to be 0.1734 2 meters. So I'll approximate C to be roughly 20 centimeters. Okay. And if I take that, then B is nothing but 1.2 meters. So you're going to have a wingspan of 1.2 meters and you are going to have a chord length of 20 centimeters of 0.2 meters. This will give you a wing area of 0.24 meters square. Okay. Does anyone have any doubt in this? So what are the data we have till now? We have the chord length with us, we have the wingspan with us, and we have the wing area with us. Okay, the wingspan area. Now I'll go back to the slides of yesterday. Now we move on to the other sizing. We have the wingspan, right? So now we have the wingspan, so we have the fuselage length. When we have the fuselage length, we have the length for all the other parts. Okay, F1, F2, F3, and the length of the horizontal stabilizer. Okay, fuselage is determined. We have the wing area already. F3 is determined during fuselage calculations. So now we know the area of the horizontal stabilizer. We know one of the dimensions of the horizontal stabilizer. We can find out the other dimension of the horizontal stabilizer. Horizontal stabilizer is sized. Now we have the vertical stabilizer. It is going to be 0.3 to 0.4 times the horizontal stabilizer area. We already have the horizontal stabilizer area, so we have the vertical stabilizer area. Now the width of the vertical stabilizer, as I told you, the width of the vertical stabilizer is roughly going to be the same as the width of the horizontal stabilizer. So again, we have another dimension of the vertical stabilizer. So we need two dimensions to form an area. We know the area of the vertical stabilizer and we know the width of the vertical stabilizer. So we can now find out the height of the vertical stabilizer. What exact shape do you want to put the horizontal and vertical stabilizer into? Right now, you can simply keep them rectangular. Okay. When you want to make advanced RC aircrafts, you will have to look into sweep. You will have to look into taper. Okay. So that is not something we are going to discuss on right now. Now let's come to the control surfaces. We can size the ailerons. We know the chord. We can find out the width of the ailerons. We know the wingspan. Can find out the length of the ailerons. The length and width are determined. So, and the ailerons have to be symmetric airfoils in nature. So it's sized. The elevators has to be 0.2 to 0.3 times the horizontal stabilizer of the area, like the area of the horizontal stabilizer. So now we have the area of the elevators and we have the length of the elevators because we know the horizontal stabilizer length. Now we can find out the breadth of the elevators. Sorry. Similarly, we have rudders and we can size the rudders. So our whole aircraft is sized now. We know the dimensions of our aircraft. We know the dimensions of the control surface. We know what battery pack to use. Okay, the battery pack you can obviously decide from what motor and prop you are using. So so battery packs are left. Yes, that's important. So now let's look at this table. So we had chosen this propeller for the motor that we were looking at, and we decided to go with the 970 configuration, right, which is going to give us. So what is the current that it is going? 3.7 at 50% throttle and 18.5 amps at 100% throttle. So I need to have a battery which at least is able to sustain 20 amperes of current. Okay. So a battery pack which provides 20 amperes and 24 volts. It is important that this motor is going to run on 24 volts. So 24 volts is roughly how much cells? 24 divided by 3.7. It's roughly 6 cells. So if you have 6 to 8 cells of battery, you can run this motor and the battery needs to minimum, sustain 20 amps of current. So now you go and Google, like if you go and search for a battery pack that is 24 volts, 20 amps in rating, you can use that battery pack. Does anyone have any doubt in the sizing and choice of components? And like now we have finally, built the RC aircraft that we want to fly. The hardware is there now. Any questions? Any doubts? If you feel that I did not cover something or some part of the aircraft is still missing, you can ask me. Okay, I'll move forward then. So the design, so now we have hit the milestone where we have, reached our, like we have made the hardware. We know what size our aircraft is going to be. We know what motor we'll be using. We know what battery we'll be using and stuff like that. So now I'll be starting with the control of the aircraft. How do you control? And this is the part that I like the most. This is my favorite part, and I have a lot of stuff to show around. We'll be seeing some good graphics also because yeah, like building an aircraft is also a lot of sweating and cutting and your hands paining. So it's a tedious exercise. But when you sit on the computer, write code, connect wires, and look at all the glory, it's really beautiful. So I have always been on the side of control more than manufacture. So that's my bias. But yeah, now we are going to discuss about control. In control, what I'm going to cover is I always obviously if you are sitting here, even if you are a second year student or a third year UG student, if you are senior, then like control theory is something which even circuital people study, mechanical people study, civil people study. So control theory is like it's embedded in all engineering disciplines. So you guys must have come across control theory at some point of the time. So I'm just going to give you a very brief overview of what controls we use in a very basic overview of what controls we use in aircrafts. Then we are going to see the manual digital transmitter receiver. How do you program it? How do you configure it? And then we are going to have a look at what do you say, the APM board, the ArduPilot board. Since you're short on time and I'm already on a Windows PC, I will not be taking up a software coding part today. Although I like in today's YouTube video that I'm going to publish online, I am going to, attach a blog post that I'll be writing today or tomorrow. And in that, you will have the complete install instructions for ROS, PX4 and Gazebo. And I really suggest that if you want to work in controls in aircraft side, then you start learning these softwares. Okay. So we'll take a break for 2 minutes right now. I'll be back and then like it's 16:20 right now. So yeah, just 16:22 I'll be back. Yeah, you'll receive an email with the YouTube link and all. Okay, don't worry about that. Okay, so let's continue with what you were doing. Um, so modeling and control. So what is modeling and what is control? Modeling is you try to describe a physical system in terms of mathematical language so that we can have a representation of it in science. That's maximum philosophical I can get. It's as simple as writing down the maths for it. So I'll take the most basic example. Um, and just taking this basic example, the reason is that either people are here who have studied control theory, then they don't need this explanation. If there are people who are not here, who have not studied control theory, then they'll only be able to understand through this explanation. So just 5 minutes of it. If you already know control theory, just bear with me. This is for the people who don't know it. So let's say we have a classic. So this is a fixed wall and this is a fixed surface. This surface does not have any friction and we have it's bad. We have a cart on top of it and we have a spring attached to it with spring constant K, and this cart has a mass M. Okay, and like this is the natural position. Okay, this is the relaxed position of the spring where the cart is. So let's label this as X naught. Okay. Now I want this cart to dance. Okay, I want it to dance in a sinusoidal fashion. Okay, and the function that I give it is that uh, the desired. So I write it X desired as a function of time is nothing but, let's say, X1 plus D sine omega t. Okay, so what am I expecting it to do, or what do I want it to do? That there is some point ahead of this X naught, right? Where this is basically, so this is X1. And what I'm expecting this card to do is I want it to, like, keep moving, like first go forward, then come backward, then again going this way. So I wanted to keep oscillating about this mean position with an amplitude D, and this is my mean position, and this is my amplitude. I wanted to keep doing that. Okay. But what will happen? Like, how can I make it do that? I want it to behave it that way, right? So how can I make it do that? I would simply, my first attempt, if I don't know any science, if I am a early human, then my first attempt would be to pull the cart and bring it to this position, right? And then I expect it to, the spring will make it jump around. But what will happen is the spring will basically take it back and crash it into the wall, because this, the value of x1 minus x naught, we don't know if it's greater than x or not, x naught or not. So that's another topic of debate, but it's not going to keep it at x1. So you probably need some force here, right? And this force is something which you are supplying, which you can control. So this is the control force that you're providing to it. And now this force is going to keep this um basically this cart in position at that place. So what is the, can we write a simple equation for this? So if this is positive x, right, and this is y, we don't need y actually, we just need the positive x. So we can simply write that the mass times acceleration is nothing but the summation of forces, which is going to be minus kx plus f. Okay. We are not concerned about friction and weight and all those things. Weight is in the perpendicular direction, friction does not exist. So now x double dot is going to be minus kx by m plus f by m. Okay. And how do we represent this in mathematics? We represent it using state vectors. Okay, vectors, you all know vectors, right? So vectors in terms of linear algebra, we represent it using linear algebraical notation. So we introduce another state called, let's say we take two states, x1, x2. We take x1 to be simply the position of the cart, which is x, and we take x1 to be the velocity of the cart. Okay. So we can simply write that dx1 by dt is equals to x2, because it is nothing but dx by dt, which is equals to x dot. And we can write dx2 by dt is nothing but x2 dot. X2 dot is nothing but dx dot by dt, which is x double dot. And x double dot is nothing but minus kx by m plus f by m. So this becomes minus kx. Now what was x? X was x1. So by m plus f by m. So if you look closely, what has become is x1 dot is equals to x2, and x2 dot is equals to minus kx1 by m plus f by m. So we have two uh, linear differential equations, and we have two variables. So we can put this in a state vector form. X1 dot x2 dot is equals to here on this side we make a matrix, we multiply it with the state vector, and we have this input force, okay, which comes out to be 0 1 f by m, and this comes out to be 0 1 minus k by m 0. So this is called the system matrix. This is called the state vector, and this is called the input vector or the control signal. So this is an overview of how we do modeling and control in the modern control theory. Okay. Now, if I were to provide you an overview of quad rotors, just hold on a second. I'll just pull up the notes that I have for today, because now it's not so straightforward. So now we learn about what are the different methods of control. The methods of control that we learn about here are the PID control. Okay. So basically what do we have is, we have this, if I take a side view of the quad rotor, this is going to be the central hub where all the PC, where all the computer and flight board is here. And we are going to have motors here, right? And these are going to be the propellers, right? And we are all similarly in this direction. We are going to have motors. Pardon me for the very 2D diagram, but let's stick with it. We are going to have motors, right? So what is the thing that we are trying to control for right now? Let's say this is the ground. So right now we want to control its distance from the ground. Okay. We just want to let it take off and, hover at some height. So again, what are the things that you need to identify in a system? The state, the system, and the inputs. So what is making it move up and down? It is these forces from these three motors, right? So these will be my inputs, and x and x dot are going to be my state vectors, right? So what is going to happen? I am going to have some desired height, and then this quadrotor is going to have some actual height, right? So there will be a difference between these two, and it is called the error term, right? This is the error, like how off I am from my desired value. Okay. And then what I can do is I can write a control law. It's the PID control law, or the right now we'll just write the PD control law first. PD control law says that you should apply an input. You should apply an input. Okay. That so since our input is a force, which is a double derivative of the position vector. Okay. So our it should be such that it should be the double derivative of our basically our desired trajectory is changing with time, so it is going to have a desired acceleration, right? So our force is going to our input is trying to bring it to that desired acceleration, so that it can also match the desired trajectory. Then we have an input term that is derivative of the error term, and then we have an input term that is proportional to the error term. So this is called the derivative control, and this is called the proportional control. So can anyone, intuitively tell me that how derivative and proportional terms, like just as an intuition, if you even if you have studied control theory, not studied, forgotten, just tell me if you have an intuition that what are these individual terms doing? Okay. Like you want a desired height, the quadrotor is at a certain height, it is off by some value, and now you are giving a force which is a function of the derivative of this error and the error itself. Do you understand the intuition behind this control law? That the input that you are giving is governed by how much error you have right now and how swiftly it is changing. Okay. For example, if let's say you are off by 1 meter, but you have very strong motors, you give it a input which is only based on the error. Okay. So the motor spins very swiftly. So, it consumes a lot of current. It's big motors. So the motor got to know, so the flight controller board got to know we are off by 1 meter. So let's give this signal to the motors. Now the motors are very fast. They bring you up, right? But what happens? Since your motors were very fast, you will probably not be able to stop at the height that you wanted to be. You'll go past that, and that your flight controller board will find out, oh, now we are half a meter above, so now we need to reduce thrust. The motors stop very quickly. So you also need to take into account, your sensors also need to keep reading that how swiftly you are moving towards the correct position. Okay. An analogous example, all of you have done machine learning. Can you just, guys, I would like to talk to a few people who have done machine learning. Is there someone who has done machine learning here? Yeah, can you just, would you like to talk directly rather than talking in the chat? Will you be up for that? Okay, there is some background noise. So, what you do in machine learning, the first algorithm that you learn is gradient descent, right? Where you have a curve, and what you are trying to do, so you see how control theory and machine learning are very related. So this is your error curve, right? You start at some point, right? and then you take the gradient descent, and that helps you move to the lower point, that helps you move to the lower point, right? And sometimes what happens is, if you are not adjusting for your step size, then you may not be able to reach here. Okay, then what will happen is, let's say you're not adjusting for your step size, then you go here, and since your step size was really huge, you come back here. Now your gradient descent tells you, oh no, you have to go in the opposite direction. So now you again come back, so now you're here. So although you will reach, or you might not also reach the minimum error point that is here, it's because you did not adjust for your step size. Why do you need to adjust for your step size? Or this is also called adjusting the momentum in gradient descent. It's to understand how close you are to the minimum point. So it's the same intuition here. The derivative control tells you that how quickly are you reaching the desired position. If you are reaching the desired position quite fast, then you need to slow down. Otherwise, you will miss the desired position. You'll overshoot from the desired position. So that is why the derivative control is very necessary. The proportional control makes sense automatically. You need proportional control because the more the error, the more force it will be required. For example, if the person is not working at all, if they are very lazy, then you need to lecture them more. Okay, if the person is less lazy, you need to lecture them less. So it's proportional. You try to understand it like this. If the error is high, you obviously need more force to correct it. But then if someone is already working towards their goal, they're reaching it, then you can't keep pestering them all the time, right? That is going to have negative consequences. So you need to take the derivative term into effect as well. So this is called PD control. So the proportional control, it basically acts as a spring response, that how much ever you press, the more error you have, the more input force you're going to give. Okay. The derivative control, it is acting as a viscous resistance. Okay. Viscous resistance, as in it's trying to, like, if you're moving towards the desired goal with the desired position with a certain rate, the derivative is trying to reduce it. It's trying to reduce it. You see, if you are moving towards your desired goal, right? What is going to happen? The error derivative, it's going to be negative. So if the error derivative is going to be negative, it's kind of going to reduce this force. So as the more faster you are reducing your error, the more negative is your error rate, error derivative, and the lesser and the more it will reduce the force, so that you don't overshoot. Okay. Now we also have something called an integral control. Okay. So this is all of this I was talking when you have a system and you are not seeing any other disturbances or stuff like that. Okay. And then you are saying that my system is isolated, I have no disturbances, then this works fantastically. It has no issues working and everything is fine. But what happens when you have disturbances? If you have disturbances, then you need to, keep a history of how your error is changing. Okay. Then you need to keep a history of how your error is changing, and that is done using the integral control. So for that, we have the whole PD control as desired, plus the derivative control, plus the proportional control, and now we also have an integral control. So integral control is nothing but Ki integral 0 to tau. Keep the limits in mind. Sorry, it's 0 to t. Keep the variables in mind. Okay. Error as a function of tau d tau. So note this, that this is all t. This is tau d tau, but it is integrated over till t. So this term, the integral term, is basically telling me what? That how much error you are having. Okay. So basically what is going to have? You are integrating the error. Okay. So if you move towards your desired goal, okay, just try to understand this. It's very easy to understand control if you just, apply basic mathematics and keep on doodling. That is, doodling is you keep making graphs and trying to. So let's say your error is reducing, okay, but the error is there, right? Your error is reducing, but your error is there. So what is going to happen? Your um, your integral control is basically going to take this much of the area into its account. Now what is happening? Let's say you reach the desired one, okay. So now your error, it might happen that your error term becomes zero, your error derivative becomes zero, okay. But then your desired trajectory, the first term, this also needs to be cancelled, right? So this gets cancelled from the with the integral term. But if your error shoots, like let's say now your error becomes negative, you have overshot the position. So now again the integral will help you in coming back. If there are external disturbances, or if there are modeling errors, integral control is going to help you get through that. Okay. Now, how do we deal with fixed wing UAVs? So this was what do I say? So this was the quad rotor UAVs. Now I will talk about the fixed wing UAVs. So fixed wing UAVs, you do not have. You means I will not give you the specific mathematical equations because they're very complex. So you need to have a proper study about that. I am suggesting something. If you want to study about flight mechanics, which is a very difficult subject coming from an aero student himself, I suggest you check out the YouTube channel of a professor called Christopher Loom. He has a 24 series or 24 videos in a playlist which talks about flight dynamics, wind tunnel testing, everything practical you need to know about how a fixed wing aircraft flies, how it is tested. Okay. It is this where you want to, garner that knowledge. Now coming to the important part, that again, I told you, if you have anything to control, what do you need to find out? The state, what is my system metrics, and what are the inputs that I am giving, or how I am. So state is telling me, like, the state variables. So the state, or the variables determining my state is telling me how the system, where the system is, what the system is doing. Okay. So for fixed wing UAVs, we have roughly 12 state variables. Don't get scared. Okay. So there are 12 state variables. They are the oil, like four of them, six of them are angles, and six of them, sorry, basically three of them are positions, three of them are angles, and then we have their derivatives. So you have x, y, z, you have phi, theta, psi, then you have x dot, y dot, z dot, phi dot, theta dot, psi dot. So this is a 12 variable state vector for fixed wing UAVs. Now I think you will be able to appreciate more why I had been telling you since yesterday or since last day's workshop that it's much more difficult to control a fixed wing UAV. Okay. So it's not that quad rotors don't have a lot of state variables, but now you'll see why. So quad rotors only have four inputs, the four motors that you have. The system matrix, it's not something you can calculate. You obviously have to measure the mass. You have to measure the mass of the system, the inertia and all that. You have to study in detail. So it's system specific. It's empirical, not something you derive mathematically. You measure it. System matrix is a value. What are the inputs? Okay. So what are the inputs? How can you control this aircraft? So first of all, what is the throttle you're providing? Delta is used to denote throttle. Okay. Then after throttle, what next can you do? You obviously have the control surfaces. That is ailerons, elevators, rudder. Okay. So these are the four primary inputs that you are going to give. But then these primary inputs have different effects on these. So you have four inputs, primary inputs, which are going to affect the 12 state variables very differently in a very complex manner. The equations are highly coupled, but for RC aircraft, you don't need to worry about this right now. You just need to have an intuition of how the aircraft is going to fly. Okay. Now I'm going to talk about manual control and automatic control quickly, and I'm going to give a review about the same. So basically, this is how basically I'll just enlarge I'll just enlarge my video. I don't know if you can enlarge the video. I think this is the best I can do. So yeah, so this is a receiver. Okay, as you can see on the screen. Um, these are called sticks. Okay, so these sticks are moving in one direction, two direction, one direction, another direction. So these are controlled by channels. So as you can see, I'll show you. So there is rudder, aileron, or throttle, elevator. Okay, so basically this stick here is used to control the throttle and the elevator, and this one is here to control the elevator, and this one is to control the rudder. Okay, so basically to give you an intuition why we do this, so basically this direction we have ailerons. Why? Because it makes the aircraft go like this direction we have rudder because it makes the aircraft yaw. This is the elevator because it makes the aircraft pitch. And this we have to, we have to keep it pulled down at this level so that it's zero throttle, and then we slowly release it to go up to 100 throttle. Okay, these are the power buttons, and then you get other functionalities on your remote, on your transmitter. So just give me 1 minute. I'll reposition my camera and you'll have a much better view of how this transmitter works. Yeah. So I guess, yeah, now you have a pretty good idea of how this transmitter looks. Okay. So these are the stick inputs that we can give from this transmitter. And then we have these switches here. So this is switch A, B, C, D. Switch A and D, the last two switches are bi-directional switches or bi-positional switches. Um, we generally use this switch A, to create a fail-safe for throttle. That is, if like when we mount or when we arm the ESC or the motor to the battery, in the transmitter, we keep this switch off so that until and unless we switch this on, you don't have to worry about the motors turning on their own. We can use similarly, you can use this one for some other purpose, for some other fail-safe purposes. These two switches in the center, they are tri-positional switches. So this is one position, this is another, and this is third. This can be used to, position flaps. Like for example, the flaps can have three various positions, and you can position flaps. Generally, only very advanced RC aircrafts have flaps. Okay. So now I'll show you. Okay, also we have these switches, these like spring potentiometers on the edges. Okay, we can use this also to send control signals. And at the back also we have we have two buttons, so you can use this to switch on or switch off. So these are push buttons. So this is FSI6, Fly Sky FSI6. This is available at MN Faruqi Center. If any one of you wants to go and work on drones or on, RC cars or RC drovers, this is a really nice advanced transmitter available at MNFIC Tinkering Lab. So I'll just switch it on. So it looks like a robot having two eyes and a big fat mouth. So you see there is this is the screen, and to unlock it, to start flying, you have to keep pressed. I need to press this for some time, and it unlocks the whole controller. So now let's focus on the screen. Okay. So So if you look closely, first of all, what is important here is that you don't need to worry about fly mode and all. This is advanced stuff. You can look it up in the manual later. Um, you have two timers in this, timer one, timer two. You can program this. Okay. Okay. So you can tap on the timers and program it. Now you here, what is important is you have TX and RX. So TX is the battery level for transmitter, and RX is shows a question mark right now. Okay. So now what I'll do is I'll show you what a receiver looks like. So this is what FSI6. Oh, sorry. This is what an FSI6 receiver looks like. And if you look closely, there are 6 channels of communication on this. I guess there are 6. 1, 2, 3. Oh, sorry. There are 10 channels of communication on this. Okay. And I don't know if it's going to focus it or not, but there are 11 ports here, 10 channels for communication. There is one channel for PWM or PPH, and then there is one channel specifically dedicated for power supplies. Okay. So you can send 10 inputs from your transmitter to your receiver, 10 different inputs. Okay. That what it means. You can independently send 10 input signals from the transmitter to this receiver. Okay. Now, how do you connect the receiver to the transmitter? You need to power it up. For powering it up, we obviously need something called a battery pack. So this is a custom battery pack that I have made. I did not have so there are really nice better battery packs by Orange at the lab back in ITKGP, but I am anyways, I did not wanted to invest 4,000 5,000 rupees in buying a battery for myself. So I bought these cheap lipo cells, and I made a rechargeable battery of my own. So this is again an 11.1 volt battery, but it does not have a lot of capacity. It's only 2000 mAh, so it discharges quite fast. But this is just for demonstration purposes. And as I told you, these are the power connectors. So the red wire is the positive one, the black wire is the negative one. So this is a DT D8060, I guess. Let's just have a quick look. It's in the battery pack section. So I told you that this is a XT90 connector. Okay. So sorry, this is an XT60 connector. So this is an XT60 connector, and this is a lead which goes into the charger. This is the balance lead. So it has one ground and 3 positives for, I put it into a balance charger, and it ensures that 3 of my cells which are here get charged, and they are all equally charged. So now what I am going to do is I am going to show you the ESC, which also has a battery eliminator circuit with it. So these 3 terminals go into the motor, these 2 connect with the battery, and this one goes to the receiver. Okay. So as I told you, I'll take you back to the diagram of the ESC. So yeah, so as you can see here, this one goes to the motor. Okay, this connection. Then this connection goes to the receiver. Okay, and these three wires. Sorry, I'm absolutely sorry. So I messed up the. So this one goes to the battery. Okay, this one goes to the receiver, and then these three wires which control the three different windings on the motor go to the motor. Okay, so now what I am going to do is now I am going to simply connect the battery with the ESC, and you won't hear anything. um, that was a false press. And now I am going to connect um, this into channel number 2. Yeah, so always keep in mind that these are three wires. The brown one is ground. Okay, the brown one is ground, the red one is positive 5 volts, and the yellow one is the control signal. So we have three wires, and I plug it into channel number. I should simply plug it into the. I'll simply plug it into the power, the one dedicated for power right now. So I'll just plug it in. And if you see, the receiver has lit up and it's not blinking right now. When you buy a new receiver, you can just Google up how do you bind. You need to bind your receiver to this transmitter. This transmitter should somehow know that you're sending signals to this specific receiver. Otherwise, there could be hundreds of RC aircrafts flying in the same area and you could, interfere with someone else's flying. So this receiver needs to be bound to this transmitter, and this red light is constant right now because it has been bound to this transmitter. So if you look at the transmitter now, the transmitter shows you that the RX, the receiver is connected and its battery is half, roughly 50%. Okay. Now you can simply, explore the settings of the transmitter, and you can go inside and, you know, I'll make a separate video for how do you work on your transmitter, how can you decide functions, how can you decide system functions. So you get all of these options, to control your aircraft using um and RC transmitter and an RC receiver. So this was how you manually control your um aircraft using an RC transmitter and an RC receiver. Now I am going to show you what does an autopilot, or how does, I'm going to give you an overview of what autonomous control architecture do you need to control your drone. Or I know we are overshooting time a little bit, but only a small part is left, and that's the most exciting part. I want to introduce you to that part, so just let me reconfigure my camera. I'll just reconfigure it. Yeah. So I'll give you an overview of the autonomous control and why I am so insistent that you at least know about this overview, because we are generally taught a lot of theory in the curriculum, but what to do exactly we do not know. So this is how the whole autonomous control architecture looks like. So obviously, you are going to have your flight board. Okay, so the most important part is the flight board, which is going to control your motors, your servos, and everything. Okay. This flight board can communicate with the companion computer. A companion computer is a completely different thing. So it can be, so basically this is an Intel NUC, this is a Jetson Nano. So these basically run Linux as their OS. They are full operating computers. Okay. Just like you have a Linux PC or you have a Windows PC, they are full operating computers running Linux, and they are meant to do the extra processing that you need to do. For example, you are doing deep learning and you are taking a, you are videographing the road, and you are instantly making a decision in which direction to fly. So it needs a huge amount of computation, even if it's trained beforehand. This companion computer is generally, communicating with external sensors such as LiDAR, camera, IR sensors. These are non-critical sensors. It's not like your aircraft cannot fly without these. It can definitely fly without these, but these sensors add certain features and functionalities to your aircraft. Moving on, your flight board basically controls your aircraft using these critical flight sensors. What are these critical flight sensors? It's the accelerometer, the gyrometer, the gyroscope, the barometer, GPS, 3D LiDAR. Okay. So these are the critical sensors which give you the state information. The information received from these sensors is what makes up that state vector I was talking about. X, Y, Z, X dot, Y dot, Z dot, phi, theta, psi, phi dot, theta dot, psi dot. Okay. Then obviously now um, you have all of this going in the air on the aircraft, and the aircraft is flying. So the aircraft needs to relay that information back to you on the ground, whether it's autonomously flying or not. It's not like, you can leave it to fly autonomously. It has to come back, and if something happens, you need to monitor it. So it needs to keep sending data back to you. That it does through its telemetry radio unit. Okay. That is why we have the telemetry radio for. And this telemetry radio keeps communicating with a software called ground control station. Ground control station is a software. It's not like you need to physically set up a ground control station. You just need a laptop, and either you need Q ground control QGC, or you need the APM mission planner. I'll just show you a short demo of the APM mission planner right now. And then moving on, I have one of the flight controller boards with me. So this is an ArduCopter autopilot. Okay. So this is, if you want to get started into autonomous flight, this is quite costly actually. This is $6,000. So if you really want to go into like drones and UAVs, I think you should get an ArduCopter. APM 2.8 is the latest one. I don't think if they've launched APM 2.9. But if they have, you should buy the latest one every time. And what this is doing is, if you look at it, if you look at the board itself, I guess you can see that there are input ports, there are output ports, there is telemetry port, there is GPS, there is a place to store memory, like there is a small memory size. You can add external, like you can add its communication to the companion computer, you can add its communication to the what's a to the to some other processing board. For example, you may have a Raspberry Pi doing some computation, you can connect it to ArduCopter. So you can do a lot of stuff using this board. And you will be surprised that this is an Arduino Mega 2650 board customized to become an autopilot. Okay. It was built on an ArduPilot 2560, and I'll show you that it shows out to be that. And basically, this is how you provide the inputs to this ArduPilot. This configuration is for ArduPlane or fixed wing aircrafts. And just now we'll see how does it look like on your ground station. So I have mission planner installed on my PC, and just give me a sec. So I'll just close everything that's unnecessary. I'll share my screen. I guess my screen is visible. Yeah, it's visible. So mission planner is an app you can simply get from the ArduPilot website. And you need to have a micro B connector. So the ArduPilot has a USB port, USB micro B port on this side. Okay. And I hope you can see so this is a ground control station software. So you install this on your PC, and now when you connect the autopilot to it, you'll be able to program it and you'll be able to retrieve a lot of data from it. So now I am simply inserting this micro USB B port into the autopilot, and you see the it starts to blink. Okay, it's switched on. So now what I'm going to do is, if you look here, you have to select COM4 Arduino Mega 2560. Like if you have done Arduino programming before, you need to specifically provide the port to the software, and you set the baud rate to 11500, and then you press on connect. Okay, so you'll see that it is connecting to the board, and it is successfully connected. And yeah, and I think it's loading the initial parameters. So these are all the parameters, like for example, motor speed, position, yaw. So now if you look, I already have some I already have some data coming up here. It tells me that the altitude is minus 0.34, the ground speed is 0. Okay. So this is all error data from my previous programming that is fed onto the board. So every time I start it, I need to calibrate it. Like every time a board is installed, it should be calibrated. So now if I lift it up, you can see that the altitude changes, and now I'm in the positive altitude. And now if I put it down, the altitude changes. Okay. And if you see, it's telling me, it's giving me an error here that the RC is not calibrated. So you'll have to calibrate it. And this is the horizon, the ground horizon in front of you, the virtual horizon. If I tilt my ArduPilot, so I'll just put it up in the screen. I don't know if it'll answer. So yeah, so now this is the forward direction. I'm holding it in. So now if I tilt it up, then you see that's how a pilot, that's what a pilot is seeing. They see the horizon go down. If you pitch the aircraft nose down, you'll see it go down. If you roll it up, you go it see like this. If you roll it this way, you go it really, and you can simply yaw it. The yaw angle changes. Okay. So you can use this to um, basically control your aircraft and monitor it. You can basically load your software or your mission plan right from the beginning onto this board, and it will simply follow that mission plan. Or even if you are using RC control, you can you can parallelly also put an RC control, and if you want to switch to manual mode from your from your pre-planned path, you can do that as well. So yeah, this was all about the workshop. We are done with the contents of the workshop. If anyone wants to ask any questions, or if anyone wants to say anything, then you are you are free to ask it right now.